So far, we've used calculus to find what's called the first derivative of y with respect to x, which is what we've been referring to as the gradient function. So we've typically been looking at quadratics, and we've used calculus to find the gradient function, which enables us to find the gradient at any point. We've looked at more complicated functions and how we can use the quotient rule, product rule, and chain rule to find the first derivative. Sometimes, however, it's useful for us to find what's called the second derivative, or in effect, the gradient of the gradient function. For instance, later on we'll go on and look at how we can use the second derivative to establish whether we have a maximum or a minimum point, or simply a point of inflection. The second derivative can be termed f dash dash x, or d squared y over dx squared. Similarly, we could have the third derivative of y with respect to x, which is just the gradient of this, which is written as f dash 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 x, or d cubed y over dx cubed. So we'll look at the notation in a minute on how this arises, but just first of all note that these second derivative and the third derivative are examples of higher order derivatives. So in terms of notation, if we want to find the gradient of a function, we've been using the notation dy by dx. But if we want to find the gradient of the gradient function, it's going to be dy by dx, or just, if we multiply these out, d squared y over dx squared, which is how we get this. And similarly here, for the third derivative, it would be d over d by dx of this function, which would then, if we multiply it out, give us d cubed y over dx squared, but equally acceptable to use this notation. The one point to be, if you go beyond f dash dash dash, it gets a little bit long and complicated just to read it all out, so we would tend to write it as f to the 4 of x. So here we've got a function fx equals x to the 4 plus 3x squared plus x. What I want you to do is to find the first three derivatives of fx, and then I want you to try and figure out the name of the actor who could be associated with the fourth derivative of this. And the first person who posts a picture of the actor on the OLP will win a prize next lesson. So pause the video now and have a quick go at that, and then we'll go through it. So here is our function fx equals x to the 4 plus 3x squared plus x. Our first derivative is what we've been doing recently, so that's straightforward. 4x cubed plus 6x plus 1. F dash dash x, we just need to differentiate each of these using the power rule and the addition rule. So we can see that's going to be 12x squared plus 6. F dash 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 x is 24x, so I will leave you to post your answer to this one on the OLP. As an extension, you might want to have a look at a graph of distance against time and think about what f dash dash x would actually be. Here, if we've got distance against time, the gradient would be dd by dt. The gradient of this would be ddd by dt, all by dt, which would be d squared d over dt all squared, which we would measure using meters per second squared, which represents acceleration. So here are the three questions for you to have a go at. Try and work your way through these, and then I'll go through them with you. Part B then, you're asked to find f dash dash x. However, you're given f dash x already, so it's asking you to find the derivative of this function here. So the first thing you need to do is use rational exponents to express this without the square root sign. So if you could do that, you get x squared plus 4 all to the power a half. So you should be thinking that to differentiate this, you're going to end up using the chain rule. So remember the chain rule here, if you want to think of this as u would be x to the power a half. So when you differentiate that, you would get a half x to the power negative half. But inside the brackets is our second function v, which is x squared plus 4. We therefore multiply this by the derivative of v. This is then going to be our second derivative, f dash dash x. We can just tidy that up and express it using a square root sign rather than rational exponents to give us this. For part C then, we're asked to find the third derivative of this function and find the value when x equals 1. So for this, we've got 4e to the power 2x. So again, we're going to have to use the chain rule here. So you can think of this as 4e to the power x. So if we differentiated that, that would be exactly the same. Using the constant multiple rule here, this would be 4 times e to the power x. However, we know that our second function, v of x, is 2x, so it's going to be 4e to the power 2x multiplied by the derivative of this, which is 2, which gives us 8e to the power 2x. We then need to find the second derivative, so again use the chain rule, and that is going to be, if you want to think about it as 8e to the power x. If we differentiate that, it would still be 8e to the power x, but v of x, our second function, is 2x. So the power is 2x, and we multiply that by the derivative, which is going to give us 16e to the 2x. The third derivative, similarly, is going to give us 32e to the 2x, and we are asked to find the third derivative for when x equals 1. So we substitute in 1 for x, which yields 32e squared. For part D, here the first derivative is going to be minus 32t plus 16, so the second derivative is just going to be minus 32.